Now that we've completed our study of statistics, for the remainder of StatCamp, what we're going to be doing is studying probability. And why are we going to do that? Because probability helps us make decisions under uncertainty. By that I mean we are often faced with making a decision today facing some kind of uncertain future. And whenever that happens, you want to think about using probability to help you make a better decision. So let me give you a few examples. You're running a company that produces computers, and you have to make a production decision right now. How many computers am I going to produce this month? But you're facing an uncertain future because you don't know your demand. It's uncertain. But you still have to make a decision today. Here's another example. You sell, let's say, health insurance. You have to set the premium that a customer has to pay you today. You have to offer the customer a premium. But you don't know what's going to happen in the future with this customer, how much money they're going to claim from your company. These are examples of making decisions facing an uncertain future. We call that decision-making under uncertainty. And whenever that happens, I hope you will think about using probability, because that's the mathematical way to help us make better decisions facing an uncertain future. So what exactly is a probability? A probability is a number. It's a number that reflects the likelihood of an event occurring. So first of all, it's useful when we are uncertain about whether the event will or will not occur. And it's measured on a scale from 0 to 1. Basically, the closer the number is to 1, the more likely that event will happen. The closer the probability is to 0, the less likely that event is going to happen. In fact, if the probability is 0, the event is not going to happen. If the probability is 1, the event will definitely happen. And just as an example, if the probability is 0.5, it's equally likely to happen or not happen. So probability is a very simple thing. It's a number between 0 and 1 associated with an event occurring. The basis for all of probability theory is what we call an experiment. An experiment is a situation where you can do an action over and over again, and each time you do it, you might get a different outcome. So exactly one of the outcomes is going to occur, but you don't know which one. Let me give you some examples of experiments. The most simple one is, of course, flipping a coin. Now, that's an action that I can do over and over again, and each time, one of two things is going to happen. You don't have to be a genius to guess what. It's going to be heads or tails. Those are the two outcomes. Another example, roll a die. That's an action I can take over and over again, and every time I roll a die, I'm going to get an outcome, but I don't know which one. So what are the possible outcomes? Well, die has 6 numbers on it, so any of the numbers 1 through 6. Those are the 6 outcomes for a die. Here's another one. Make a sales call. What might happen? What 2 things might happen? You might either make the sale or not make the sale. So those are the outcomes. Here's the one that's a little bit more challenging. The Dow Jones Industrial Average tomorrow. Again, that's an action that can happen over and over again. Every day we get a new value for the Dow Jones Industrial Average. So what are the possible outcomes? Now, you might think up and down. Well, that is true. The Dow Jones Industrial might go up or it might go down. If that's all you're interested in, then those 2 outcomes would be what we would write here. But I'm actually interested in the numerical value of the Dow Jones tomorrow. So what are the possible values that it could be? It can't be any number, but it could be any positive number. Those are all the possible outcomes, and there's a lot of them. I hope these examples are helpful to you to understand that an experiment is an action that gets repeated over and over again, each time resulting in one of a number of possible outcomes, and you don't know which outcome is actually going to occur. For discussion purposes, let's say we're going to do an experiment that has, let's say, n possible outcomes, and I'm going to name these outcomes E1, E2, E3, En. We have n outcomes possible. After you identify the experiment, that is, the action that you're going to take over and over again and what the possible outcomes are, the next thing you have to do is assign probabilities to these outcomes. We can do nothing until you assign probabilities to these outcomes. And that's got to be a number between 0 and 1 for each outcome. So I'm going to tell you a little bit about how to do that in just a moment. But every probability of each event is going to be a number between 0 and 1. And when you add up all the probabilities of all the events, you should end up with exactly 1. In mathematics, the probability of E1 plus the probability of E2 plus the probability of En, add up all the probabilities of the events, must be equal to 1. Again, we set it up by identifying an experiment and the outcomes, but then we have to get a probability for every outcome. How can we get the probabilities? Well, it turns out that there are 3 different ways that we can assign probabilities to these outcomes. The first way is what we call the classical method. It's based on the assumption that all of the outcomes are equally likely. For example, flipping a coin, a fair coin. Heads, tails, they're equally likely. Rolling a die. There are 6 outcomes. If the die is fair, they're all equally likely. If that is your situation, then you can assign probabilities by this classical method, and I'll show you how to do that in a moment. But unfortunately, not all experiments have outcomes that are equally likely. It may be that some of the outcomes are more likely to occur than some of the other outcomes. And then we still need the probabilities, but the way we get that is very much based on our past data. If we can collect past data on how often each of these outcomes has occurred in the past, we can use that relative frequency method to estimate the probabilities of each of the outcomes. And again, I'll show you how to do this with an example. Now, failing data, that is, if we don't have data from the past of how likely these outcomes or how often these outcomes occurred in the past, and we can't use the equally likely assumption, we still need probabilities, and about the only thing left to us is what we call the subjective method. This is where you make a personal judgment, hopefully based on your best knowledge, maybe some consultation with an expert. Get your best estimate of the likelihoods of these outcomes occurring. So these are the 3 methods that we use to assign probabilities. Either the classical method, where all the outcomes are equally likely, or if they're not all equally likely, hopefully we can get some past data on how often each of the outcomes has occurred in the past. That's the relative frequency method. Or failing that, use your best judgment, the subjective method. Okay, so now let's talk about this classical method. This is where all of the outcomes are equally likely. So how do we assign probabilities to each of the outcomes in this case? Well, the answer turns out to be very simple. If you have n outcomes, then the probability of every one of them is 1 over n. And the question is, why is that true? And that I'm going to show you right now. So here's the question. Let's suppose you have a probability experiment, and let's just say that there are n outcomes. Let's give them some names. Let's say E1, outcome E1, outcome E2, and so on down to outcome En. All right, so now what we want to do is say, suppose they are all equally likely to occur. What is the probability of any one of them occurring? Well, we have n probabilities here. They're all equal because they're equally likely. So let's give them a label. Let's call them x. This is x. All of these are x. They're all the same number because they're all equally likely. How do we figure out what the value of x is? What is the probability of any one of these occurring? Well, we have to use one more piece of knowledge. Whatever the value of x is, when you add up these probabilities, you better get the magic number 1. That is a necessary fact for an experiment. The sum of the probabilities of all the outcomes must be equal to 1. So that means this plus this plus this must be equal to 1. Well, let's look at this. We are adding up the same number how many times? 1, 2, 3, 4, 5, n times. So this whole thing is equal to n times x. Well, let's just solve this for x. Divide both sides by n, and you get the magic number x equals 1 over n. And let me summarize what this is saying. If you have an experiment with n outcomes, and they're all equally likely, so this probability is the same as this probability is the same as this probability, what is the probability that any one of these occurs? The answer is right there, 1 over n. Let me give you some examples of equally likely. We discussed it before, but let me give you some examples. Okay, we're going to toss a coin. There are 2 possible outcomes. N is 2. So what is the probability of heads and the probability of tails? 1 over n, 1 over 2, 1/2. In decimal form, 0.5. Either one is fine. Here's another example. We're going to roll a die. We have 6 possible outcomes. Assuming the die is fair, they're all equally likely. So what is the probability of any one of them? Well, in this case, n is 6. We have 6 outcomes, 1 over 6. Each outcome has a chance of 1 over 6 of occurring. So the equally likely method is really simple. If you have n outcomes, the probability of any one of those outcomes occurring is 1 over n. If you cannot use the equally likely assumption because it's not necessarily true that all of the outcomes are equally likely, then the next best thing we can hope to do is have some data, get some data on the fraction of times in the past that these outcomes have occurred. Those fractions of time that the outcomes have occurred in the past, those become our best estimates of the probabilities of the outcomes going forward in the future. So let me give you an example. Suppose we are going to be asking people about what they think about some new law. And these people are going to answer with one of these possibilities. They're either going to disagree with the new law, they're going to be neutral about the new law, they're going to agree with it, or they've never heard of this old new law, so we're going to call them uninformed. So here we have some outcomes. And if they were equally likely, can somebody out there tell me what the probability of any one of them occurring is? I don't hear you. Oh, that's because I'm in the studio. Okay, so there's 4 outcomes, so equally likely, 1 out of 4. But unfortunately, these outcomes in this particular problem are not equally likely. So how can we get the probabilities of these outcomes occurring? Well, let's take a survey. Let's collect some data. So what we've done here is we've gone out and we've asked 127 people what they think about this law. And we've collected their answers, and we've summarized their answers with descriptive statistics in the form of a frequency distribution. So what you see here is out of the 127 people, 52 answered that they disagree with the law, 12 answered that they were neutral, 37 agreed, and 26 were uninformed. That's the frequency distribution, the frequency table. For probabilities, we need to convert these numbers into the relative frequencies, which you see here in the last column. So for example, if we're looking at the outcome disagree, 52 out of 127 is 0.41. For the neutral outcome, 12 out of 127 is 0.09. 37 out of 127 is 0.29 for agree, and for uninformed, 26 out of 127 is 0.21. Those relative frequencies from the data become our best estimates of the probabilities of these outcomes occurring, shall we say, in the future. So based on this relative frequency distribution, I would say that my best estimate of the probability of somebody disagreeing with this law is 0.41. The probability of somebody being neutral is 0.09. The probability of somebody agreeing is 0.29. And the probability that somebody is uninformed is 0.21. So this is by far the best way to estimate probabilities of outcomes when they're not equally likely. However, unfortunately, in some situations, we either don't have this data or we cannot get it. And if that happens, well, we're sort of stuck a little bit, but we still need these probabilities of the outcomes. There's no getting around it. So what we would use in that case is what we call the subjective method. This is where you use your best knowledge to estimate these probabilities. So again, you should only use this method when the equally likely assumption is not appropriate, doesn't work for your problem, and when you cannot get data. Then you should think about the subjective method, base it on whatever your knowledge of the situation is. You might call in an expert to help you get good probabilities, but we've got to come up with these numbers. So keep in mind, though, that whatever numbers you do assign by this method, they are your personal belief. Somebody else might have a very different belief in the probabilities of these outcomes. Let me give you an example of that. So I've got a job offer, and the question is, what is the probability that I'll get that job offer? Well, from my perspective, I might believe that it's equally likely, 50-50. But our career office, they're much more optimistic. They think there's a 70% chance that I'll get the offer and a 30% chance that I don't. So again, subjective probabilities are exactly that. They're subjective.